In the previous lecture, we were discussing about the impulse response and the convolution sum, using which we can get the response of the system to any arbitrary input signal x of n. Now, let us quickly recall what do we mean by impulse response. The impulse response is the response of the system to when the input is a unit impulse function. So if we have an LTI system to which the input signal is a unit impulse function, that is delta of n, whatever output we get as a response to that unit impulse as our input, that is called as the impulse response. And the impulse response is denoted, the accepted norm, okay, that is generally followed for representing the impulse response is the letter h. So h of n denotes the output of the system when the input is a unit impulse function, and that h of n is called as the impulse response of this system. So this h of n is called as the impulse response. Okay, now if we know the impulse response of the system h of n, then we can find the output of that system to any input x of n by the knowledge of the impulse response h of n. So for any arbitrary input x of n, we can find the output y of n as the convolution between the input x of n and the impulse response h of n. The star operation denotes the convolution operation, which is defined as let me write that, y of n equals x of n convolved with the impulse response h of n, which is defined as, it's called as the convolution sum, which is summation x of k into h of n minus k for k equals minus infinity to infinity. Now this is called as the convolution sum, and we have seen up to this point in the last lecture. Okay, I'm just recapping what we did in the last lecture. So we had covered up to this equation in the last lecture, and this is a very important fundamental equation in the analysis of systems. Okay, so the output of the system to any arbitrary input x of n is equal to the convolution of the input with the impulse response of the system. So if we know the impulse response of the system, then we can find the response of the system to any input signal x of n. That is what it means. Okay, now graphically illustrating this, the impulse response is basically when the input is a unit impulse like this. Okay, when the input signal is a unit impulse, the output, whatever output we get for the system, that is called as the impulse response, which we denote as h of n. So I've given an example here where the input is an impulse function. That means it is having a value of 1 when n equal to 0. For all other values of n, the value of the signal is 0. So it is existing only for n equal to 0. Right, and at n equal to 0, it has a height of 1. Okay, so that's called as a unit impulse function. When we apply this as an input to the LTI system, whatever output we get, we call that as the impulse response. And here I have given an example for an impulse response. Let's say we have it like this, and we'll use this example for the impulse response in further example in our further analysis and understanding of the convolution operation. So what we have on the right here is basically the impulse response of this system. So basically when the input is this delta of n, this is the output we get. Okay, now the system is a time invariant system, linear time invariant system. Now what do we mean by time invariant? Again, recall from a couple of lectures back, one of the properties that the time invariant system will satisfy is that if the input is shifted by a certain amount, then the output will also be shifted by the same amount. So when the input is delta of n, the output is h of n. So if the input gets shifted to the right by a certain amount, let's say by 1 sample unit, so if the input is delta of n minus 1, then the output will also be shifted by 1 to the right. That means that when the input is delta of n minus 1, the output should be h of n minus 1. That is when the time invariance property is satisfied. So let's illustrate that as well. So now what I have depicted here is a shifted impulse. So let's say when the input is delta of n, we get this output h of n, which is the impulse response of the system. Now we have a shifted impulse. The impulse is shifted to the right by 1. So the impulse occurs at n equal to 1. So that is denoted as delta of n minus 1. So minus here indicates a right shift by 1. So this impulse is shifted to the right by 1. What will be the corresponding output? And since we say that this system is a linear time invariant system, for a time invariant system, any shift in the input, okay, if we have shifted this delta n and made it delta of n minus 1, will produce a corresponding shift in the output as well. So when the input is delta of n, the output is h of n. And similarly, for a time invariant system, if the input is delta of n minus 1, which is delta of n shifted to the right by 1, the corresponding output will be this h of n also shifted to the right by 1. So we will plot this. So basically all of these samples will get shifted to the right by 1 time unit, which is 1 unit of n. So what we will get as output is h of n minus 1, that is h of n shifted to the right by 1. So what we see here on the right here is the output of the system to a shifted impulse. So when this impulse is shifted to the right by 1, the impulse response is also shifted to the right by 1. So what we have here is h of n minus 1 basically. Okay, so let me write that correctly. So that will be in relation to h of n, that is equal to h of n minus 1. So when the input is shifted to the right by a certain amount, the output is also shifted by the same amount, okay, and in the same direction. So we see here whatever was at minus 1, okay, that has got shifted to the right and it has come to 0. The value that was present at 0, that has got shifted to the right and has come to 1. The value that was at 1, that has got shifted to the right and come at 2. The value at 2 has moved to 3, and the value that was at 3 has moved to 4, and the value that was at 4 has moved to 5. Similarly, the value at minus 2 has moved to minus 1. The value of minus 3 has moved to minus 2. And similarly, the value of minus 4 will move to minus 3 and so on. So, and these dots here indicate that it is 0 beyond 4 and beyond minus 3 on the left. Okay, so basically at minus 3 also it's going to be 0, because anything beyond minus 3 is also 0, and anything beyond 4 is also 0. Okay, so basically what we see here is that when the input is shifted to the right by a certain amount, the output is also shifted to the right by the same amount. If this input was shifted to the left, for example, this delta of n was shifted to the left and it was at minus 1, then h of n will also be shifted. The entire sequence will be shifted to the left by the same amount. Okay, so if we had delta of n plus 1, that would be an impulse at n equal to minus 1, then the corresponding output would be h of n plus 1, which is h of n shifted to the left by 1. So h of n minus 1 is shifted to the right by 1 time unit. Okay, now similarly we can get the output of the shifted impulse once we know the impulse response of the system. So whatever is the shift in this impulse, the corresponding shift will be seen in the impulse response as well. The output will also be shifted by the same amount and in the same direction. If this is shifted to the right by 5, then this also will be shifted to the right by 5 samples. And if this is shifted to the left by, say, for example, 3, then h of n will also be shifted to the left by 3. So basically that arises from the property of time invariance. Okay, that is what we mean by time invariance. In a time invariant system, any shift in the input will produce a corresponding shift in the output signal as well. Now we are going to use this idea to understand what the convolution operation is doing. Okay, what the convolution is doing, and how do we interpret the output of the system in terms of the convolution between the input and the impulse response of the system. So what we're basically saying is that when the input is delta of n, the output is h of n. When the input is delta of n minus 1, the output is h of n minus 1. So a shift to the right in delta of n produces a shift to the right in h of n as well. Okay, so that's the input-output relationship. So when the input is delta of n minus 1, the output is also h of n minus 1. Okay, now we'll see the example when the input is shifted to the left. What will be the output? That will be the output h of n shifted to the left by 1 as well, if we have the impulse shifted to the left by 1. So I will now illustrate what happens when it is shifted to the left, just for clarity purposes. So again, I have shown here the original impulse and the impulse response. Now if this impulse is shifted to the left by a certain amount, then this entire impulse response will also be shifted to the left by the same amount. And for illustration purposes, I'm going to shift this to the left by 2 samples. So we'll put an impulse here to the left at n equal to -2. So that's basically at -2. So that's n, and that is delta of n plus 2. That means the impulse that we have, the unit impulse signal that we have on top here, has been shifted to the left by 2 samples. So it is delta of n plus 2. That means the impulse is present at n equal to -2. And if this is given as input to the signal, then what will be the corresponding output? So when the input is delta of n, we get h of n. When the input is delta of n plus 2, that is delta of n shifted to the left by 2, the output that we get will also be h of n shifted to the left by 2 sample units. So whatever is occurring at -3 will get shifted to the left by 2. So each of these samples will get shifted to the left by 2 time units. So what is occurring at -3 will go to -5. The value at -2 will go to -4, and so on. So let's mark the axis values. So that's 0, 1, 2, 3, 4, 5, -1, -2, -3, -4, and -5. So the value at -3 will appear at -5 because it is shifted to the left by 2. The value at -2 will occur at -4. So that's -2 shifted to the left by 2. The value at -1 will come to n equal to -3. So we will have it like this at -3. So let me erase this. I'm going to draw the line first and then write the sample value. So whatever is occurring at -1, that is now occurring at -3 because it is shifted to the left by 2 sample units. The value at 0 will occur at -2. So this term at 0 is shifted to the left by 2. So we'll get it like this here. Whatever is 1 will appear at -1. So the value at 1, which is this value, that gets shifted to the left by 2. So we get that at -1. The value at 2 comes to 0. So we'll get that here. Okay. And the value that is at 3 in h of n, that will come at 1. So we'll get this here. And the value at 4 comes at 2, and the value at 5 will come to 3, and so on. All right, so this is basically h of n plus 2. H of n plus 2. So what we see here is that when the input is shifted by a certain amount to the left, the output h of n is also shifted to the left by the same amount. Okay, delta of n plus 2 produces h of n plus 2, and that is the property of time invariance. Okay, any shift in the input produces a corresponding shift in the output as well. Okay, now this is the whole idea behind convolution. It's exactly scale shifted impulse responses added together, and that is what I want to illustrate. So what we see is that if we know the impulse response of the system, then we can find the output of the system to any input by performing the convolution between the input and the impulse response. And when we perform that convolution, what we'll see is that we will come across these shifted versions of the impulse response, shifted to the right or shifted to the left, as in this case. Okay, and then we are going to add up all these impulse responses together to get the overall impulse response of the system. Okay, and that is why I'm illustrating these shifts that we are seeing here. So you need to remember for a time invariant system, any shift in the input produces a corresponding shift in the output, and that is something we have discussed in detail a couple of lectures back when we talked about the properties of systems. Okay, now we are going to use those things in our understanding of convolution now. Let us now perform the convolution operation between an input signal x of n and the impulse response h of n that we have seen here, and try to understand what is the response of the system. So I'm going to do this step by step so that you can get a clear picture of what exactly is happening in convolution, and then in the tutorial you will see how to perform the convolution between any two sequences. Okay, but you need to have a clear understanding of what this convolution actually means. Okay, so I'm going to illustrate that with this example. So I'm going to use this impulse response h of n, the same impulse response that we have here, this h of n, and we'll use some x of n as well. So now for simplicity, I have chosen the signal x of n. This example is from the textbook, where we have non-zero values of x of n only for n equal to -1, 0, and +1. For n greater than 1 and for n less than -1, all the sample values are equal to 0. Okay, there's only 3 non-zero values here, which are at -1, 0, and +1. Okay, we've just taken it for simplicity, and the impulse response is exactly what we had on the previous examples, which is this impulse response. So now we want to find the output of the system. So we know that the impulse response of the system is this h of n, and we now want to apply this x of n as input and find what will be the output of the system to this input signal x of n. And from the equation of convolution, we can write the output y of n as the convolution between x of n. Okay, convolution is given by the star symbol. Okay, convolution of x of n with the impulse response h of n, which is equal to summation x of k into h of n minus k for k equals -infinity to infinity. So we are going to basically substitute k equal to -infinity and so on. So basically what we see is that for k below -2 is 0. So x of -3 into h of n minus -3, that will be h of n plus 3, right? When k equal to -2, we'll get x of -2, which is this point, into h of n minus -2, which will become h of n plus 2. When k equal to -1, we'll get x of -1 into h of n plus 1. When k equal to 0, we'll get x of 0 into h of n minus 0, which is h of 0, which is h of n, which is basically this. Okay, so basically we are going to take each of these samples and multiply or scale the impulse response h of n, shifted versions of h of n, by the values of the input signal. So when k is -3, it is x of -3 multiplying h of n plus 3, that is h of n shifted to the left by 3. Okay, but since x of -3 is 0, this product with all of these 0 into anything is going to be 0. So we're going to scale the impulse response with each of these input signal values, and we are going to use shifted versions of this impulse response h of n. Okay, that is exactly what we're going to do. So since since x of n is 0 for all other values other than for n equal to -1, 0, and 1, so this term is non-zero only when k equal to -1, 0, and 1. Okay, for all other values it is 0, so 0 into anything is 0. So this summation basically has only 3 terms now, which is for k equal to -1, for k equal to 0, and for k equal to +1. Okay, so let me write that. Since x of k equal to 0 for, or let me rephrase that, it is not equal to 0 only for k equal to -1, 0, and 1. So this summation y of n is basically x of -1 into h of n minus -1, which is n minus of -1 is n plus 1, plus x of 0 into h of n minus 0, which is n, plus x of 1 into h of n minus 1, that is n minus k, right? N minus 1. Here k is equal to 1. So we have only these three terms: x of -1, x of 0, which is this, and x of +1, which is this. These are the three terms in x of n which are non-zero. For all other values of n, x of n is 0. So in this summation, all other products of these terms become 0. So it's like adding +0, +0, +0. So we need to write only these three terms now. So what we see is that the output y of n is going to be x of 0 multiplied with the h of n. That means the impulse response h of n is scaled by the value of x of 0. The value at x equal to -1 is scaling a left shifted version of the impulse response. So we take h of n, shift it to the left by 1, and scale it by the value of x at n equal to -1. Similarly, here it is h of n minus 1, that is the right shifted version of the impulse response, scaled by x of 1, and then we add all of these to get our output y of n. Okay, so I'm going to show each of these step by step. Okay, so the first term is h of n plus 1, that is this h of n shifted to the left by 1 and scaled by x of -1, that is each of these terms will be multiplied with the value at n equal to -1 for x of n. Okay, so x of -1 times h of n plus 1. So let's plot that first term. So I'm going to plot each of these terms, and then we will add these together to get our output of the system y of n. So I've illustrated these shifted versions of the impulse response h of n plus 1, h of n, and h of n minus 1 in the next slide. So we take this original h of n, and h of n plus 1 is this h of n shifted to the left by 1, and h of n minus 1 is h of n shifted to the right by 1, okay, which is exactly what I've shown here. So we have this original h of n here, and what is on top here is h of n plus 1. We see that it is shifted to the left. This is h of n. This h of n has been shifted to the left by 1, and this is h of n minus 1, which is h of n shifted to the right by 1. Okay, and it continues beyond those values. Okay, similarly here. Now the output of the system that we have as per our equation is scaled versions of these shifted impulse responses, where this h of n plus 1 is scaled by x of minus 1. It is scaled by this value of x of minus 1, and h of n is scaled by the value of x of 0, and h of n minus 1 is scaled by the value of x of 1, and then all these scaled impulse responses are added together to get the overall response of the system to the input x of n. Okay, so I have shown here the original shifted impulse responses. So our output y of n equals x of minus 1 times h of n plus 1. Now what is x of minus 1? From our diagram for the a signal x of n, I'm going to show that here also. So that's, let me write the equation first, plus x of 0 times h of n plus x of 1 times h of n minus 1. So let me show you what. Let me plot the signal x of n also on the same page, so you can see exactly what's happening. So here I have depicted our input signal x of n. So from this we know that we can find that x of minus 1 is equal to minus 2, x of 0 equals 1, and x of 1 equals plus 2. So in place of x of minus 1, x of 0, and x of 1, we're just going to put these values of x of n at those values of n. So therefore our output y of n becomes x of minus 1, which is minus 2 times h of n plus 1, because x of minus 1 is this value, which is having a value of minus 2, plus x of 0 is 1, 1 times h of n, so it is simply h of, let me write it on top itself, we have enough space here, so that's plus h of n plus x of 1. X of 1 is having a value of 2, okay, which is this one, so it's 2 times h of n minus 1 plus 2 times h of n minus 1. So basically what we have to do now is we have to take each of these shifted impulse responses and scale it by these factors. So we'll take this h of n plus 1 and scale it by minus 2. That means each of these sample values will get multiplied with minus 2. That will give us minus 2 times h of n plus 1. Similarly, h of n is getting multiplied with 1 because x of 0 is 1. So we'll have it as it is, this term. And h of n minus 1 will get scaled by a factor 2. So all these terms will get multiplied with 2. So they'll get scaled up by a factor of 2. So I'm going to illustrate that as well in my next slide, and then we'll add up all those terms to get our impulse to get our response of our system y of n. And before I show the scaling, I need to scale the y-axis also. So like here, h of n, okay, the first line, this is having a height of 1 and this is having a height of 2, right? So I need to mark these also on this page. So that's 1, that's 2, that's minus 1. Similarly, that's 1, 2, and that's minus 1. And here also that's 2, that's 1, and that's minus 1. Okay, so we have these original amplitudes of the impulse response. Now we are going to scale these by the respective amount. Okay, the respective amounts of scaling is minus 2 for h of n plus 1, 1 for h of n, and plus 2 for h of n minus 1. So we are going to scale each of these by the corresponding amounts. So that means we are going to multiply h of n plus 1 with minus 2. We are going to multiply h of n with 1, which is this, and we are going to multiply h of n minus 1 with 2. So that is what we are going to do. So we'll take those multiplications and show the scaled versions of these shifted impulse responses. So now we are going to scale h of n plus 1 by minus 2. That means each of these samples will get multiplied with minus 2. So when n equal to minus 4, so minus 2 into 0, the value here is 0. So minus 2 into 0 will remain 0. So for n equal to minus 4, it is minus 2 into 0 is 0. For minus 3 also, it is minus 2 into 0 is 0. And when n equal to minus 2, the value here is minus 1. So this minus 1 gets multiplied with minus 2. So minus 1 into minus 2 will become plus 2. So we will have it in the positive direction now. So this will be in the positive direction, like this, with a height of 2. So if I can call this as 2, and when n equal to minus 1, the value is 2. So 2 multiplied with minus 2 will make it minus 4, right? So the value here at n equal to minus 1 is plus 2. that gets multiplied with minus 2. Plus 2 into minus 2 is minus 4. So when n equal to minus 1, we'll get something like this, which is minus 4. And when n equal to 0, the value here is 1. This 1 gets multiplied with minus 2. So 1 into minus 2 will be minus 2. So that will be like this. And when n equal to 1, that's 0. 0 into minus 2 will be 0. When n equal to 2, the value is 1. So this 1 gets multiplied with minus 2. So 1 into minus 2 will get minus 2 again, so which is here. And when n equal to 3, the value is 0. 0 into minus 2 will be 0 as well. So we'll have it like this. And anything beyond that is also going to be 0, because h of n is 0 beyond 4, right? Okay, so any other value further is also 0. Okay, I'm not showing that here, so it is continuing with zeros beyond that. So these are the this is the scaled and shifted impulse response. So that's for n equal to 0, 1, 2, 3. That's for n equal to minus 1, minus 2, minus 3, minus 4. And the heights now, when n equal to minus 1, that's 2. Okay, that's minus 1. So that's minus 1, minus 2, minus 3, and then we'll have minus 4 over here. Okay, so we see that this is the scaled and shifted impulse response, where the scaling is done or the scaling factor is x of minus 1. Okay, because the scaling factor is x of minus 1, and x of minus 1 is equal to minus 2. So that's why we have multiplied h of n plus 1 with minus 2, scaled h of n plus 1 by a factor of minus 2. So each of these samples has got multiplied with minus 2, and we get this which is nothing but minus 2 times. So that's n on the x-axis, and that is minus 2 times h of n plus 1. Okay, similarly, the second term that we have in our summation here is plus h of n, because x of 0 is 1. 1 times h of n is h of n. So we'll have this h of n as it is. So we have now put the h of n as it is over here. So it is 1 times h of n, which is h of n. So it's just a copy of h of n now. Now h of n minus 1 is scaled by a factor 2, because x of 1 is equal to 2, which is this sample here. So we have to multiply this h of n minus 1 by 2, that is scale it by a factor of 2. So basically we are going to write it as 2 times h of n minus 1. Okay, that's 2 times h of n minus 1. So basically what will happen is each of these samples of h of n minus 1 will get multiplied by a factor 2. So their heights will get doubled basically. Okay, and we'll plot that now. And then finally we have to add all of these shifted impulse responses to get our overall response of our system. Okay, so let us now scale this h of n minus 1 by a factor of 2. That means each of these samples will get multiplied by 2. So when n equal to minus 3, minus 2, and minus 1, the value of h of n minus 1, for these values of minus 3 here, the value of h of n minus 1 is 0. So these get multiplied with 2, so 0 into 2 remains 0 for all those 3 terms. So we'll have still as 0, 0, and 0 for minus 1, minus 2, and minus 3. For n equal to 0, that is for this value here, we have the value is minus 1. So minus 1 gets multiplied by 2, so we'll get it as minus 2. So 2 into minus 1, we'll get it as now it is scaled up. Okay, so now it is having a height of -2, so that's -2, so that's -1 here. So -1 has got doubled to -2, and when n equal to 1, the value of h of n minus 1 is 2 here. So 2 into 2 will become 4, so we'll get an impulse here of height 1 2 3, that's 4 here. And for n equal to 2, the original value is 1. 1 times 2 will become 2, so we'll have it as at height of 2 here. For n equal to 3, it is 0, so 0 into 2 is 0. For n equal to 4, the value in h of n minus 1 is 1, so 1 into 2 will become 2, so we'll have it as 2 for this as well. And for n equal to 5, it's 0. 0 into 2 is again 0, and anything else will further be 0 as well. Okay, so now we have this as 4, so that's our 2 now, that's -2. Okay, so that's 1 2 3 4. So this is the scaled version of h of n minus 1, where the scaling factor is 2. And let me mark the x-axis values as well, the rest of the values. So that's 1, that's 2, that's 3, 4, 5, and that's for 0. Okay, so what we have here is n on the x-axis, and 2 times h of n minus 1 on the y-axis. Okay, so I've made this h of n pretty small here because it's just a copy of this. Okay, so this h of n is just a copy of this. Now what we have to do is we need to add these three together to get y of n, because y of n is x of -1 times h of n plus 1. Okay, which is basically the summation here, -2 times h of n plus 1 plus h of n plus 2 times h of n minus 1, which we have here. Okay, all these three plots are here. We just need to add these three sample by sample, and that will give us our y of n. So I'm just going to shift this h of n slightly and put it in alignment here, and then we will add these terms together. Okay, I'm just going to so we will now add these terms and get our overall output y of n for the input x of n. So now to find the output, all we have to do is add these three scaled impulse responses, because our y of n is -2 times h of n plus 1 plus h of n plus 2 times h of n minus 1, which is the sum of these three plots. Okay, so we basically have to take each index value, and corresponding to that index value, whatever is the sample value in each of these three plots, we have to add it and get the index value for y of n. So now we have for n equal to -4. So when n equal to -4 in the first plot, in this plot, it is 0. For n equal to -4 in h of n is also 0, because anything beyond this is also 0. That's what these dots indicate. So that's also 0. So 0 plus 0, and here also it's 0. For n equal to -4, we are going to get 0. So n equal to -4 is, that's -1, -2, -3, -4 to here, the fourth point here. Now, so that's equal to 0. So for n equal to -4, we get y of n equal to 0. For n equal to -3, so we're just going to add all the values at n equal to -3 in these three plots. So at n equal to -3, here it's 0, and here also it's 0, and here also it's 0. So that's also 0. That's for n equal to -3. For n equals -2, here we have a value of 2. Here we have 0. So that's 2 plus 0. And here is also 0. So 2 plus 0 plus 0. So that should be 2. So now we'll get a height of an impulse of height 2 in this case. So for n equal to 2, we get an impulse of height 2. So that's our y-axis values. So that's 1, that's 2, that's 3, 4, 5, and so on. Similarly here, minus 1, minus 2, it's minus 2, minus 3, minus 4, and so on. Okay, so for n equal to minus 2, we get 2 plus 0 plus 0, which is 2. Okay, and for n equal to minus 1, so when n equal to minus 1, here we have minus 4, here we have minus 1, so that value here is minus 1, right? So that's minus 4 plus minus 1, and for the third graph it is 0, so minus 4 minus 1, which is this value, plus 0, so that's minus 5. So we'll get it as minus 5 over here. That will be an impulse having a value of minus 5 at n equal to minus 1. That's minus 5, and that's at n equal to minus 1. That's n on the x-axis. So when n equal to minus 1, let me repeat that. When n equal to minus 1, for the first graph, we have a value of minus 4. For the h of n, we have as minus 1. So minus 4 plus minus 1 is minus 5. And for 2 times h of n minus 1 is 0. So that's minus 4 minus 1 plus 0, which is minus 5. So we have got this for our the value of y of n at n equal to minus 1. When n equal to 0, we need to add all the terms at n equal to 0. So here we have minus 2, and for h of n we have plus 2, right? So that's 1 and that's 2. So that's minus 2 plus 2, that's 0, and here we have also minus 2. So it's minus 2 plus 2 minus 2, which is minus 2. So we'll get an impulse of height minus 2 when n equal to 0. So now we have the value of the sample, output sample, at n equal to 0 as well. For n equal to 1, we'll just add these terms. When n equal to 1, the first signal has a value of 0. H of n is having a value of 1, so that's 0 plus 1 plus this is having 4. So that's 0 plus 1 plus 4 is going to be 5. So for n equal to 1, it will be an impulse of height 5. So up to here. So that's for n equal to 1, an impulse of height 5. For n equal to 2, we have here minus 2. For n equal to 2, we have here 0. So that's minus 2 plus 0. And for n equal to 2, we have here plus 2. So that's a minus 2 plus 0. And that's a plus 2. So minus 2 plus 0 plus 2 is 0. Okay, because minus 2 and plus 2 will cancel out now. So that's for n equal to 2, we have minus 2, 0, and plus 2. So the sum is 0. So for n equal to 2, we get y of 2 is 0. And for n equal to 3, we have 0. And in h of n, we have 1. So that's 0 plus 1 is 1 plus 0. So 0 plus 1 plus 0 is 1. So for n equal to 3, we'll have an impulse of height 1. That's for n equal to 3. Now for n equal to 4, here, okay, this dotted line, these dots here indicate that anything beyond 3 is 0. So that's 0. Here also it's 0. So that's 0 plus 0 plus 2. So here the value for n equal to 4 is 2. So 0 plus 0 plus 2 is 2. So for n equal to 4, we have an impulse of height 2. So that's for n equal to 4. And for n equal to 5, Again, n equal to 5 here is 0, n equal to 5 here also is 0, and here also is 0. So it's 0, and anything beyond that is all zeros, right? So 0 plus 0, everything will be zeros. So that's for n equal to 5, 6, and so on. Okay, and it continues beyond that. Okay, so what we have plotted now here is our output y of n for the input x of n that we started off with. Okay, so when we know that the impulse response is this h of n, then the output y of n when the input is a certain x of n, as we have taken in this example, is given by this final figure that we have here, which is this particular y of n. Okay, so the output that we have got here is the output of the system y of the system when the input is x of n. And how did we do this? We computed this output by performing the convolution between the input x of n and the impulse response h of n. So basically what this convolution operation is showing is that it is finding the contribution of each of the input samples. Okay, it is finding out what is the contribution of the value of x of 0 on the output, on the overall output y of n. Okay, how much of this value is contributing for each sample of the output y of n. So what is the contribution of x of 0 to y of 0, y of 1, y of 2, y of minus 1, y of minus 2, and so on? What is the contribution of x of 1 to every sample of y? What is the contribution of x of minus 1 to every sample of y? And it is taking all those contributions and adding them all together to get the overall response of the system. That is basically what convolution is doing. So it is basically the sum of scaled and shifted impulse responses of the system. That's what the convolution is producing, and that way we are able to compute the overall output of the system for any arbitrary input of the system, given the knowledge of the impulse response of the system. So if we know the impulse response of the system, we can compute the response of the system to any arbitrary input by performing the convolution between the input signal and the impulse response of the system. Okay, and this is what we have got here. So what we have done here is basically we have obtained this y of n by adding these three plots, which are nothing but the scaled and shifted versions of the impulse response. That's our original impulse response h of n. That's the impulse response shifted to the left by 1 and scaled by a factor -2. And that's the impulse response, this h of n, shifted to the right by 1 and scaled by a factor of 2. So adding these terms, okay, has given us, okay, when we have added these together, we have got the output y of n, and that is basically what the convolution operation is doing. Okay, and I would like you to look at the examples in the textbooks. Okay, look closely at example 2.1 and example 2.2 in the textbook. So I'll okay, it is a similar example as we have done here, but I want you to look at those examples to also get more clarity on the concepts, and that way the more you practice, the better understanding you will have. And these are, as I said, very fundamental concepts, and we will be using these concepts again and again. So all these concepts of shift and time invariance that we have seen in the previous 2-3 lectures, we have used in today's lecture, right? Similarly, what we have seen in today's lecture, it will be used in future lectures. So it is important that you have a clear understanding and you remember what these concepts are. So I want you to look at the example number 2.1 in the textbook. That's example 2.1 as well as example 2.2 in the textbook, and also practice the problems given to you during the tutorials. Okay, and only then you will be familiar with these concepts, and you will find yourself comfortable dealing with these concepts. Okay, so I'm going to write down that you need to do the exercise. Okay, that's example 2.1 and example 2.2 from your textbook, okay, which is the textbook of Oppenheim and Wilsky. Okay, example 2.1 is on page number what is the page number? Page number 80, and example 2.2 is on page number 81. Okay, that's page 80, and that's example 2.2 from page 81. Okay, so you need to look at these two examples, which is very similar to the example that I've given here, and try to get a better understanding of the process of convolution. And as I said before, you need to practice the problems given in the tutorial class as well. Okay, we'll stop here for today, and in the next lecture I will be extending these ideas to the continuous time. Okay, so far we have been talking about the convolution here, and we are discussing only about convolution in terms of the discrete time. Okay, in the next lecture I'm going to extend these ideas to the continuous time signal, where we will define what is the impulse response of a continuous time system and what is the output of a continuous time system given its impulse response. Again, we will see the convolution operation in the continuous time domain as well. Okay, so that will be the discussion that we'll have in the next lecture. And again, since I have discussed in detail the concept of convolution and impulse response in the discrete time domain, our discussion on continuous time will be much more rapid, and because you have a reasonable understanding of what this process is with examples from the discrete time. Okay, so when we do the continuous time version, it will be going much faster because it is just an extension of these ideas. Okay, wherever there is a critical difference, that will be pointed out to you, but since the concepts have been laid out very clearly, we'll be going through the concepts of continuous time, impulse response, and continuous time convolution at a much faster rate. Okay, we'll stop here for today, and we'll continue in the next lecture.